In today's lecture, I'm going to discuss potential energy and conservation of energy. In chapter 7, I discussed the work done by the gravitational force and also the work done by a spring force. In this lecture today, we are going to see how those works are related to the change in gravitational potential energy and elastic potential energy. I will also discuss the principle of conservation of energy and the role of non-conservative forces in that principle. Let's begin with the definition of potential energy. Potential energy, U, is energy that can be associated with the configuration of a system of objects that exert forces on one another. A system of objects may be Earth and a bungee jumper or any falling object. So for this system we have two different types of potential energy present. We have gravitational potential energy, which accounts for the kinetic energy increase during the fall. And then we also have elastic potential energy, which accounts for the deceleration by the bungee cord. A different type of system could be an object free falling towards the ground. In this particular case, we only have gravitational potential energy. A different example would be from the previous chapter, from chapter 7, the block that I discussed connected to a spring and then the other end of the spring being attached to not be able to move. So in this example, the block will oscillate horizontally, and in that example, we have elastic potential energy only. In all those examples, we have a specific force, such as gravitational force or the spring force, doing work, and as a result, the potential energy of the system is changing. The specifics of the physics problem determines how potential energy is calculated to account for stored energy. The general relationship between the change of potential energy and the work done is given by this formula, where the change in potential energy is equal to negative of the work done by the particular force in the system. Here we have an example of two systems. We have an object that is thrown above ground and the ground itself. And here we have a different system, which is a block attached to a spring that can oscillate left and right horizontally. Let's first look at the tomato Earth system here. So as the tomato is being tossed up in the air, it starts with some initial velocity, which means that it possesses some kinetic energy after it leaves the hand of the person that tosses it up in the air. So we know that as the tomato is going up in the air, it's slowing down until eventually it will stop. So that means that the tomato is losing kinetic energy. The kinetic energy decreases as the tomato is going up. So then what happens to that kinetic energy? We know that energy cannot be destroyed, therefore it must be converting into a different type of energy. And what happens is the kinetic energy of the tomato decreases, but then the gravitational potential energy of the tomato increases. So the kinetic energy is being transferred from the tomato by the gravitational force into the gravitational potential energy of the tomato. So one more time, the kinetic energy decreases as the tomato is going up, but the gravitational potential energy, the kinetic energy of the tomato decreases as the tomato is going up, but the gravitational potential energy of the tomato increases as the tomato is going up. Once the tomato reaches the highest point here, it stops for an instant of time, and then it starts to fall back down towards ground. So now what happens is the kinetic energy of the tomato increases from 0 to a value that it will get as it hits the ground or lands in the hand of that person. So the kinetic energy increases, which means that this increase must come from somewhere. The increase comes from the decrease of the gravitational potential energy of the tomato. So at the very top here, the tomato has a maximum amount of gravitational potential energy with respect to the ground. And so as it's falling down, the gravitational potential energy will be decreasing. So the gravitational potential energy is leaving the tomato, and the gravitational force is transferring that gravitational potential energy into the kinetic energy of the tomato. So during the entire motion of the tomato, initially we have maximum kinetic energy, which decreases as the tomato is going up. At the same time, the gravitational potential energy of the tomato increases as it's going up. When the tomato reaches the highest point, it stops for an instant of time and then it starts to fall down. So the gravitational potential energy now decreases as the tomato goes down, and the kinetic energy of the tomato increases as the tomato is going down. Now let's look at the work done by the gravitational force. On its way up, the gravitational force does negative work on the tomato. So the change in gravitational potential energy, which will be positive since at the highest point the gravitational potential energy is more than at the lowest point. So this change will be equal to the negative of the work done by the gravitational force. And we know that from the previous chapter that for an object that is going upward, the gravitational force does negative work. Now, as the tomato is falling down, the work done by the gravitational force is positive, but the change in gravitational potential energy is negative because at the highest point, the gravitational potential energy is more than at the lowest point. And so this statement right here holds for this system, tomato Earth. Now let's also look at the other system, which is the block spring system. So if the block is pushed to the right, that is going to compress the spring, which then produces a spring force that is directed to the left. And so this spring force is going to transfer kinetic energy from the block towards the elastic potential energy of the spring. What does that mean? Well, the block simply slows down as it displaces to the right until it will momentarily be at rest. At this point, the spring is maximally compressed, which means that the maximum amount of elastic potential energy is stored in the spring. After that, the spring starts to push on the block, so that stored elastic potential energy now is used to move the block. As a result, the elastic potential energy of the spring decreases, but then the kinetic energy of the block increases. And so, again, the change in elastic potential energy for the spring is equal to minus the work done by the spring force. The same thing happens for the other direction of motion of the block, to the left. As the block is moving to the left, the spring is starting to get stretched, and so a spring force then appears directed to the right, which is going to do work on the block, and it will slow it down. It will essentially transfer the kinetic energy of the block into the elastic potential energy of the spring. The block stops for an instant when the spring is maximally stretched, and then all the elastic potential energy stored in the spring is going to be then used to accelerate the block back to the right. And this energy will then be transferred to the block as kinetic energy. So we here have a conversion between kinetic energy of the block and elastic potential energy of the spring. We know that the work done by the spring force is always negative. So therefore, the change in elastic potential energy of the spring is related to the work done by the spring force by that same expression. Let's summarize in general what happens in a system similar to the two systems that I discussed on the previous slide. So first, the system consists of two or more objects. A force acts between a particle, for example, the tomato or the block, and the rest of the system. So here the force was, in the tomato example, the gravitational force, in the block example, the spring force. When the configuration changes, the force does work W1, changing kinetic energy to another form of energy. When the configuration change is reversed, the force reverses the energy transfer, doing work W2, and so then changing that other form of energy, which was gravitational potential energy or elastic potential energy, back to kinetic energy. So thus the kinetic energy of the tomato block becomes potential energy and then kinetic energy again. Let's get into more detail as far as the force that acts between the particle and the rest of the system is concerned. We've discussed several different specific forces in the previous chapters. We talked about gravitational force, we talked about the force of friction, tension, so on and so forth. In terms of the energy transfer inside the system, the forces that I just mentioned separate into two categories: conservative forces and non-conservative forces. Conservative forces are forces for which the work done when the kinetic energy is changed to a different type of energy is equal to the negative of the work done when this other type of energy is changed back to kinetic energy. And this is always true. Examples of such conservative forces are the gravitational force and the spring force. For those two forces, the transfer or the change of kinetic energy into potential energy and then back from potential energy to kinetic energy is reversible. For non-conservative forces, the transfer of energy from kinetic to potential and then back from potential to kinetic is not reversible. So for non-conservative forces, this condition is true. The works done to convert kinetic energy to another form of energy is not equal to the work done to convert that other form of energy to kinetic energy. The process is not reversible. Example of non-conservative forces are kinetic friction force and drag force. Why are these forces examples of forces for which forces that do work which is not reversible? Because when kinetic friction is at play, heat is generated. So kinetic energy of a moving particle is transferred to heat by the force of friction. And as we know, heat is lost in the surroundings. We also know that if we reverse the process, so if we slide the block to the right, we lose some kinetic energy in the form of heat. Now, if we slide the block to the left, the same amount of distance, that heat is not going to be recovered and converted back to kinetic energy. Instead, more heat will be generated, and so as a result, more kinetic energy will be lost. So thermal energy cannot be recovered back into kinetic energy of the object via the friction force. So therefore, this force is non-conservative. It does not conserve the energy. Thermal energy is not a potential energy. So there is an important consequence of the relationship between transfer of energy and conservative forces. When only conservative forces act on a particle, we find many problems can be simplified, because the net work done by a conservative force on a particle moving around any closed path is zero. And also, the work done by a conservative force on a particle moving between 2 points does not depend on the path taken by the particle. Let's explain the first statement on the previous slide. The net work done by a conservative force on a particle moving around any closed path is zero. Consider a particle with mass m at this initial position. I want to bring this particle to that final position. And then I want to take it from the final position, bring it back to the initial position. So I'm going to do that using two different paths. Here are my two paths. Path number 1 is in blue, and it looks like so. And that is the path that the particle takes from its initial position to the final position. And then path number 2 in purple is like so. That is the path that the particle takes from the final position to the initial position. Let's calculate the work done along each path, and let's see if they're equal to each other. So for path number 1, the work that we are going to consider here is the work done by the gravitational force. So the gravitational force is always directed straight down towards ground. As the particle is moving along the horizontal portions of the path, the gravitational force does no work. The gravitational force only will do work along the vertical portions of the path. Let's label the vertical portions with y1, y2, and y3. And so then the work done along the three vertical portions is, so the work done by the gravitational force is Wg, that is equal to the gravitational force times y1 cosine of theta, which is 0 degrees. That's the angle between the gravitational force and the vertical displacement down, plus Fg times y2 cosine of 0, plus Fg y3 cosine of 0. So that is Fg times y1 plus y2 plus y3. Now let's calculate the work done by the gravitational force as the particle is moving from the final position to the initial position along path number 2. As the particle is moving along the horizontal portion of path number 2, the gravitational force does no work. The gravitational force does work only along the vertical part of the path. So let's calculate the work done by the gravitational force there. So the work done by the gravitational force along path 2 is Fg times y, where y is the vertical displacement along path 2. Okay, but now notice that the vertical displacement along path 2 is equal to the sum of this vertical displacements along path 1. So y1 plus y2 plus y3. However, the work done along path 2 moving up here will also be determined by the cosine of the angle between the gravitational force and the displacement. And so this angle is 180 degrees. So cosine of 180. So this is equal to negative Fgy. So here then we can compare the two works done. And we find out that they are equal in magnitude, opposite in signs, of course. So Wg1 is equal to minus Wg2. So then the net work done along this closed path, like so, will be equal to Wg1 plus Wg2, and this is equal to 0. And that is the statement that I made at the beginning. The net work done by a conservative force on a particle moving around any closed path is 0. The second statement on the previous slide was that the work done by a conservative force on a particle moving between 2 points does not depend on the path taken by the particle. I can discuss this using the same example. The particle starts from this initial position, gets to this final position. Now, what I want to do is, I want to take path number 1 the way I took it already. I also want to get from the initial position to the final position along path 2, which means that I'll have to reverse the arrows here. So instead of redrawing everything, I'm just going to use different color to illustrate path 2 for that second statement. Let's go with bright green. So the particle is going to go along path 3, like so, from the initial position to the final position. So we know that when the particle is moving from the initial to the final positions along path 1, the work done by the gravitational force is simply Fg times y1 plus y2 plus y3. As the particle is moving now along path 3, first goes down, the vertical displacement is equal to the sum of these displacements along path 1. So the gravitational force will do the same amount of work as along path 1. The horizontal portion of the path here, along that portion of the path, the gravitational force does no work. So I have two different paths that the particle took between the initial and final positions, and along those two different paths, the gravitational force did the same work. So again, that confirms that the work done by a conservative force on a particle moving between 2 points does not depend on the path taken by the particle. So then for 2 points in space A and B, I can say that the work done between A and B along path 1, WAB1, is equal to the work done between A and B along path 2, or that is WAB2. This property can be used to solve problems where the actual path between the 2 points is complicated. For example, like so. So this is a complicated path trajectory that calculating the work over that will require integration. Instead, using this property, I can select an alternative path over which the object will get from point A to point B, which is much easier to calculate the work done during that motion, and it will produce the same result as if the object moved along the original path between the 2 points. For the general case of calculating the work done by a force as a function of position, the work done by the force is calculated by this integral. The work is equal to the integral from some initial position and to some final position of the force as a function of position, dx. Then using the relationship between work and change in potential energy, delta U is equal to minus W, I can write an integral for the change in potential energy in terms of the force. And so that expression is that delta U is equal to minus the integral of the work. Let's calculate the expression for the gravitational potential energy using the formulas from the previous slide. So the general relationship between the change in potential energy and force is given by this integral here. Since I'm going to discuss gravitational potential energy, I will change the variables from x to y since we have vertical motion. Then the expression becomes delta U is equal to minus an integral from y initial to y final, f of y dy. F of y is simply the gravitational force, and this is equal to minus mg, because the gravitational force always points in negative y direction, since we select positive y to be always up. Let's substitute in the integral. The integral then becomes minus an integral from y initial to y final of minus mg dy. Since mg is a constant, it can come in front of the integral. So then the integral becomes mg integral of yi to yf dy, which simply becomes mgy, and the limits will be y initial to y final, which becomes mg y final minus y initial. In this form, the change in gravitational potential energy depends on the difference between two vertical positions of the object as it's moving up in the above ground. Now let's rename the variables to simplify the expression. Let's rename the final vertical position YF, simply Y. And let's rename the initial vertical position Y initial to become a 0. And we are going to call this the reference position. So at this position, the potential energy, gravitational potential energy initial will be equal to 0. So then in that notation, what we are doing is we are measuring the gravitational potential energy with respect to that reference position. So then the change in gravitational potential energy will be written as U final minus U initial. In terms of our new labeling, this will become simply U minus 0, and that will be equal to mgy. And so U as a function of y equal to mgy is what we define as gravitational potential energy of the moving object. Or for short, this is GPE, gravitational potential energy. So when we are calculating gravitational potential energy, we need to determine our reference position, or define what it is, or set it, what we want it to be. And then when we measure the distance vertically from that position, we calculate the gravitational potential energy of the object by multiplying the mass of that object by the gravitational acceleration by the vertical distance from the reference position. Keep in mind that the selection of reference position will also determine the sign of the gravitational potential energy. If the object is above the reference position, then the gravitational potential energy will be a positive number. If the object is below the reference position, then the gravitational potential energy will be negative number. The sign of the gravitational potential energy also can depend on the choice of direction of the vertical axis. So when we do example problems, and also when we do problems on the concept of gravitational potential energy, the selection of the zero reference level as well as the direction of the vertical axis will play an important role, and you have to be very careful when you're calculating gravitational potential energy in order to get the correct signs. To summarize in a statement the expression for the gravitational potential energy, we say that the gravitational potential energy associated with a particle Earth system depends only on the vertical position y, or height, of the particle relative to the reference position y equals 0, and not on the horizontal position. Similar calculation can be done for the elastic potential energy. The change in the elastic potential energy is equal to minus the work done by the spring force, which is minus kx dx. And the limits of integration are from some initial position to some final position, which then becomes the integral k times the integral of xi to xf of x dx, which is 1/2 k x squared between those two limits, which finally becomes this expression here. So the change in elastic potential energy for a system such as a block attached to a spring that can oscillate horizontally is given by this expression here. Now I can again set my reference level xi to be equal to 0, and so therefore the elastic potential energy ui at that level is equal to 0. Then I can also set my final position xf simply to be called x, and then the elastic potential energy as a function of position is given by this formula here. U of x is equal to 1/2 kx squared. This is calculated with respect to the selected zero reference level or position. Now we are ready to talk about conservation of mechanical energy. The mechanical energy of a system is the sum of its potential energy U and kinetic energy K. The mechanical energy E mechanical is equal to K plus U. Work done by conservative forces, such as the gravitational force or spring force, increases the kinetic energy and decreases the potential energy by that amount. So then we can say that the change in kinetic energy is equal to minus the change of potential energy. In other words, kinetic energy final minus kinetic energy initial is equal to minus potential energy final minus potential energy initial. I can rearrange the terms to get the following relationship. The mechanical energy initial is equal to mechanical energy final. Then I can make the following statement. In an isolated system where only conservative forces cause energy changes, the kinetic energy and potential energy can change, but their sum, the mechanical energy of the system, cannot change. So when only conservative forces act in the system, such as the gravitational force or spring force, the mechanical energy of the system doesn't change. The sum of kinetic and potential energy of the system remains constant. The individual parts, the kinetic energy and the potential energy, can change in value, but the sum remains always the same. This is known as the principle of conservation of mechanical energy. The change in mechanical energy is equal to the change in kinetic energy plus the change in potential energy, and that is equal to 0. This is only true, one more time, in the presence of conservative forces. This leads to the following statement. When the mechanical energy of a system is conserved, we can relate the sum of kinetic energy and potential energy at one instant to that at another instant without considering the intermediate motion and without finding the work done by the forces involved. Here's a very simplified example of the previous statement. Let's look at an object with mass m at some initial position. This object is being tossed up in the air with some initial velocity, v sub I, and travels up in the air until it reaches this final position where it becomes at rest. So at this final position, v final is equal to 0. The initial position will have vertical coordinate yi. The final position will have vertical coordinate yf. So I can also calculate then the mechanical energy at each of those two positions. So the mechanical energy initial will be equal to kinetic energy initial plus gravitational potential energy initial, which is simply mv initial squared divided by 2 plus mgy initial. Then at the final position, the mechanical energy mechanical final is simply kinetic energy final plus gravitational potential energy final. And this is equal to mv final squared divided by 2 plus mgy final. And now, since there is no air resistance in this particular situation, we ignore it. That means that there is no non-conservative forces in the system. There is only conservative forces, and that is the gravitational force, which is directed like so. That means that the mechanical energy initial and final must be equal. Or in other words, we can write that mv initial squared over 2 plus mgy initial is equal to mv final squared over 2 plus mgy final. Well, here now I have explicit expressions for the mechanical energy at the two positions, and now I can calculate or find any of the variables, provided that I know the others or enough information to find the others as well. And this is a very powerful tool which allows us to calculate parameters of the motion without having to know what's happening between positions. We only need to know what the parameters are at the initial and final positions, but not in between. Let's talk about reading a potential energy curve and the relationship between a force as a function of position and potential energy. In one of the previous slides, I talked about the relationship between change in potential energy and the work done by a force. And that relationship simply was that the change in potential energy is equal to the negative of the work done by the force, which can be written as minus F of x times delta x. So then from here, I can rearrange terms and solve for the force. And F of x will be equal to delta U divided by delta x. Now, if I want to calculate the force at any particular position, not in between like a position range, I have to take a limit here when delta x approaches 0. So when I do that, then I arrive at the following expression. So the force as a function of position is equal to minus the first derivative with respect to position of the potential energy function. So what does that mean? It means that if I have an explicit form of the potential energy function as a function of position, if I take the position derivative of that potential energy function with the minus sign, that's going to give me the force as a function of position that causes the object to move along that potential energy curve. We are going to do an analysis of a potential energy curve and specific points associated with the position of the moving object along that curve. But before that, we can write the mechanical energy in terms of the potential energy as a function of position and the kinetic energy as a function of position, like so. U of x plus k of x is equal to the mechanical energy. If we want to find the kinetic energy then, but when we know the mechanical energy and the value of the potential energy function at specific position, and we simply take the difference of the mechanical energy and the potential energy function at that particular position. Remember that the mechanical energy is constant for the object, so therefore it does not depend on position. Let's look at the plot of potential energy as function of position and identify some important points that are relevant for the analysis of the potential energy function and the force that causes the particle to move along the plotted trajectory. For simplifying the discussion in a way, you can think of the trajectory of the moving particle as, let's say, a wheel that rolls on a system of hills. And this, of course, is just one-dimensional currently, so we can imagine the system of hills as a one-dimensional system. So we have a wheel that rolls along those hills. Okay. E0, E1, E2, and E3 are 4 different options for the mechanical energy of this particle or wheel. So let's start with E3. This is the mechanical energy of the particle, and at all points, at all moments of time, this energy, of course, is constant because only conservative forces act on the particle. So the particle can only move between this point here where the mechanical energy level crosses the potential energy curve and this point. So anywhere in between those 2 points the particle can get when it has a mechanical energy E3. So when the particle gets to that point right here at the top of this hill, it will stop there, and this is a position of unstable equilibrium. So this is a maximum point. Another maximum point is right here. This is also a position of unstable equilibrium. So unstable equilibrium points are maxima in the potential energy curve. What does unstable equilibrium mean? It means that if the particle is right here, if I push a little bit to the right, the particle is going to roll down that hill and it's going to continue to move. It's never going to return back to that position. If I pushed on the particle to the left a little bit, it's going to roll down this hill. It's not going to go back to that equilibrium position on its own. So that's what it means. Okay, so again, when the mechanical energy of the particle is E3, then the particle is confined to move along this curve between those 2 points here and here. So that is where the particle can move. It cannot go beyond, it cannot go higher than that because it doesn't have that much energy. When it gets to this point, it's going to stop. That is unstable equilibrium. Now, what happens when the mechanical energy is equal to E2, this level? Well, the particle now is confined to move between this point and this point. So between XC, position XC and XD. So right here. The particle no longer can reach this hill here. It cannot get to that position. Okay, so it can be moving only between XC and XD along the potential energy curve. 2 more important points in the reading of the potential energy curve. The particle can end up at position X1 or position X3, which are known as stable equilibrium points. Those are the minima in the potential energy curve. What does stable equilibrium points mean? It means that if a particle is at this position and it's pushed to the left or to the right by some force, the particle is going to move up, slow down, stop, and then go back down, return to that position. So eventually the particle, after it stops moving like that left to right, will become stationary at that equilibrium position. So this is stable equilibrium. So again, unstable equilibrium was when the particle gets to the top of a hill, and then if it's pushed to left or right, it's going to roll off the hill and it's never going to return back to that initial position on its own. For stable equilibrium, it's exactly the opposite. When the particle is pushed to the left or right, eventually it's going to return to this starting position. So that's why it's stable equilibrium position. So for the particle having energy E2, mechanical energy E2, it's confined to move only between those 2 points of the potential energy curve between XC and XD. Now, if the particle has mechanical energy E1, like that, then the particle is confined to move only right here on the potential energy curve. So this is between points XA and XB. And finally, if the particle has total energy E0 right here, then it's confined to be only stationary at that point X1 at the very minimum of this curve, and it cannot move away from it. It's fixed in place. Below this plot, we have a plot of the force as a function of position. And remember, the relationship between the force and the potential energy function was that f of x is equal to minus du of x dx. This derivative here corresponds to the slope of the potential energy function at any point along the curve. So then between the beginning and point x1, the slope is negative, which then means that the force is a positive number by magnitude. So the slope is negative, but the force is positive. So that means that the force pushes the particle to move to the right. And so as you can see, the particle is going to go down this curve. Once the particle hits this minimum position, then the slope becomes positive, but the force becomes negative, meaning now there is force that pushes the particle to go to the left. So between x1 and x2, the force versus position portion of the graph looks like so. So how do we interpret that behavior of the force? Well, when the particle is here and we let go, or this wheel, it's going to roll down the hill. When it reaches the lowest position and passes it, now it will start to slow down. So here the wheel speeds up, reaches the bottom, starts to climb the hill, it slows down. So force pushes the wheel down, and once it passes the minimum position, now force pushes in opposite direction, slows down the wheel until it gets to the top here. So for the interval or the position change from x1 to x2, the force pushes to the left, the slope of the potential energy curve is positive. Now between x2 and x3, the slope of the potential energy curve is negative. The force that acts on the particle is positive and acts to the right. Force versus position plot between those 2 points, x2 and x3, is shown here. Then after that, between x3 and x4, we have force that pushes to the left. The slope is positive of the potential energy curve. So therefore, force versus position looks like that here. And then after that, after x4, the force will be positive, or to the right, the slope will be negative. And so that's what we have here. So in terms of this relationship between the force and the potential energy function as a function of position, du dx is simply the slope of the potential energy function at any position, and that is the relationship between the slope and the function. I also need to add one more terminology, and that is, what are these points here called for a particle that has mechanical energy E2 and can only move between those 2 points here and here? So imagine you have that wheel that rolls down the hill. It rolls like this, it gets to that point, it stops here, then it starts to go back, gets to this point, starts to go back, gets to this point, starts to go back, gets to this point, and so on and so forth. So those 2 points, XC and XD, are also known as turning points. So here and here we have turning points. Now let's look at the relationship for the mechanical energy. The mechanical energy of the particle is equal to the sum of the kinetic energy as a function of position plus potential energy as a function of position. So let's look at the particle having mechanical energy E2. So at point XC, all of the mechanical energy is equal to the potential energy. So that means that there is no kinetic energy at this point. As the particle goes down, it reaches this position, x1. At this point, this difference here is the potential energy of the particle, and this is the kinetic energy of the particle. The sum of the two is equal to E2. So when the particle is at position x1, this corresponds to the potential energy portion of the mechanical energy, and this will correspond to the kinetic energy part of the mechanical energy. And the sum of the two will give us the mechanical energy at x1. If the particle is right here, then this portion here will be the potential energy portion of the mechanical energy, and this will be the kinetic energy portion of the mechanical energy, and so on and so forth. At the turning points, as I said, the mechanical energy is simply equal to the potential energy. So at the turning points, the kinetic energy is equal to 0. So at the turning points, the kinetic energy is equal to 0. So now you can see how if the mechanical energy of the moving object or particle is known, the potential energy can be calculated as a function of position, and then the kinetic energy can be calculated by knowing the potential energy. And the opposite calculation is also correct, meaning if we know the mechanical energy and the kinetic energy as a function of position, one could calculate the potential energy as a function of position at that particular point. Let's expand the concept of work done within a system by a force internal for the system to work done by an external force on the entire system. Here is an example. We have a ball and Earth, and that is the system. We're going to apply external to the system force to change the mechanical energy of the system. A simple example of such force would be a person picking up the ball from the ground. So vertical force is applied, and therefore work is done by this external force, which is the force applied by the person on the ball. This force again is external to the system because it is not a force that appears between the members of the system because of the natural way they interact with each other. So then work can be defined by this external force as energy transferred to or from a system by means of external force acting on that system. So then the work done by that external force W will be equal to the change in kinetic energy plus the change of potential energy of the system, because lifting the ball transfers energy to the kinetic energy and the potential energy of the system. Or in other words, the work done by the external force will be equal to the change in mechanical energy of the system. Now notice that since the work done by the external force is not 0, the change in mechanical energy is not 0 either. Another thing that I need to point out is that in this particular example of application of external force, no friction forces are involved. So again, air resistance is ignored, and in this particular example, there is no friction. So again, when external force is applied and there are no non-conservative forces acting in the process, the work done by the external force is equal to the change in mechanical energy of the system. Now let's add friction to the discussion. For a system with friction, the change in thermal energy is equal to the work done by the friction force. And so this is the increase in thermal energy because of friction. So then the work done by external forces will be equal to the change in mechanical energy plus the change in thermal energy. Here is an example of where we have this situation. Consider this block, which is being moved to the right by applied force F. This force is external to the system being the block and the surface. As a result of the sliding of the block across the surface, a force of friction arises as well. This is a non-conservative force. So the force F does work W And this work will go towards the change of the mechanical energy of the system, and then a portion of that work will go towards the change of the thermal energy of the system, which is equal to the work done by the kinetic friction. In this particular example, because we have only horizontal motion, the work done by the applied force goes into kinetic energy and also thermal energy. On the previous slide, I talked about work done on a system, and that was equal to the change in mechanical energy of the system and the thermal energy of the system. However, I can discuss the law of conservation of energy for the total energy of the system. The total energy of the system E is the sum of the mechanical, thermal, and other internal energies. Those other internal energies could be rotational energies or vibrational energies of the members of the system. So the combination of all of these energies is known as the total energy E of the system. So then the total energy E of a system can change only by amounts of energy that are transferred to or from the system. The transfer of energy to or from the system can happen by doing work on the system. So the work done on the system is equal to the change in total energy of the system, which is equal to the change in mechanical energy plus the change in thermal energy plus the change in other internal energies of the system. So we are keeping the same ideas for conservation of energy, but now we are expanding from a system of objects and looking at their mechanical energy only to including the thermal energy of the system and also the internal energy of the system. What happens if the system is isolated from its surroundings, which means that external forces cannot be doing work on the system? In this case, the total energy E of the isolated system cannot change. It is conserved. Energy transfers may only happen internal to the system, so energy can be transferred only between members of the system. Energy cannot come from outside of the system, cannot leave the system. In this case, we say that the change in mechanical energy plus the change of thermal energy plus the change of internal energy is equal to 0. Which then means that in an isolated system, we can relate the total energy at one instant to the total energy at another instant without considering the energies at intermediate times. Now let's do a few examples applying the concepts learned in that chapter. Here's the first example. You throw a 0.145 kilogram baseball straight up, giving it an initial velocity of magnitude 20 meters per second. Find how high it goes ignoring air resistance. So here is the baseball. The mass is 0.145 kilograms. The initial velocity is 20 meters per second. It goes straight up in the air. And it stops for an instant of time at position Y2. At that position, it has speed of 0 meters per second. The question is, how high did the ball go? Basically, what is the vertical displacement here? Y2 minus Y1. So to solve this problem, I will use conservation of mechanical energy. Conservation of mechanical energy stated that kinetic energy initial plus potential energy initial will be equal to kinetic energy final plus potential energy final. Why can I use this principle? Because there is no air resistance in this problem. So explicitly, the conservation of mechanical energy relationship looks like so. I'm going to select my reference level for the potential energy to be at the initial position of the ball, which means that the potential energy at the initial position will be 0. We also know that at the highest point, the ball is stationary at rest, so therefore the final kinetic energy is also 0. So then from here, we get that mv initial squared divided by 2 is equal to mg y final. Now I can solve for y final. I also can cancel the masses here. And the expression that I get for the final position is vi squared divided by 2g. Since the initial position is 0, then the value that I will get for yf is actually the vertical distance that the ball is going to travel. Let's substitute the known values and calculate the result. So the ball goes up in the air from the release point 20.4 meters. Let's now expand the example from the previous problem to add external force to the system. Let's suppose that your hand moves upward by 0.5 meters while you are throwing the ball. The ball leaves your hand with an upward velocity of 20 meters per second. First, find the magnitude of the net force, assumed constant, that your hand exerts on the ball, and then find the speed of the ball at a point 15 meters above the point where it leaves your hand. Ignore air resistance. And so here is the drawing of the situation. The ball is in hand, moves up 50 centimeters before it's released. It's released at 20 meters per second and reaches 15 meters, at which point we want to find the speed of the ball right here. So this is not the highest point that the ball reaches. It goes beyond 15 meters above. We just want the speed of the ball at 15 meters above. This problem is an example of a problem where external force is applied to the system, and that is the force applied by the hand on the ball, the system being the ball and the ground. So in this case, the conservation of energy statement was that the work done by the external force will be equal to change in kinetic energy plus the change in gravitational potential energy. So I can then rewrite the top relationship as the work done by the external force is equal to kinetic energy final minus kinetic energy initial, which is this part, plus potential energy final minus potential energy initial, which is this part, and then I can regroup the terms to get that the work done by the external force is equal plus the kinetic energy initial plus the potential energy initial is equal to kinetic energy final plus potential energy final. Now, what are the initial energies, or at what point are they calculated? Kinetic energy initial and potential energy initial are calculated at the position where the hand starts to move up with the ball. The position where the ball is released from the hand is going to be my zero reference point, and that is the final position where the kinetic energy final and potential energy final are calculated. So, at the beginning of the whole process, the ball is stationary, so therefore the initial kinetic energy will be zero, and then the gravitational potential energy is calculated with the value for the position as negative 0.5 meters. At the final position, the gravitational potential energy will be zero because that is my reference level, and the kinetic energy will be calculated with velocity of 20 meters per second. Then I have all the information necessary to calculate the work done by the force applied by the hand. Let's do that. So the work done by the external force is equal to plus kinetic energy initial plus potential energy initial is equal to kinetic energy final plus potential energy final. The initial kinetic energy is zero because the ball is stationary in hand. The hand is not moving yet. And then the final potential energy is zero because that's where I selected my reference level. Now let's calculate the work done by the external force. So substituting all the values in this expression and calculating, I get the result for the force W is 29.7 joules. However, the question was asking what's the force that the hand applies on the ball. So in order to find the force, we just need to divide the work done by the distance that the hand travels up as it's holding the ball. So that will be, or that's the displacement, so that will be y2 minus y1. So this is equal to 29.7 joules divided by 0.5 meters. And this is equal to 59 newtons. For the second part of the question, we need to find the velocity at 15 meters above. We want to find the velocity at 15 meters above the release point. So for that, since there is no longer an external force applied to the system, we can use the conservation of mechanical energy when conservative forces are present, and that is simply the gravitational force in this case. So again, since there is no external force present anymore, the change in mechanical energy is zero, which simply means that kinetic energy initial plus potential energy initial is equal to kinetic energy final plus potential energy final. Explicitly written in terms of kinetic and potential energies, that is mv initial squared over 2 plus mg y1. And this potential energy term is zero because that is y1 is my zero reference level. This is equal to mv final squared plus mg y3, and y3 is 15 meters. So now I'm going to also cancel out the masses and rearrange the terms to solve for v final. The expression that I get for the final velocity is Vf is square root of v initial squared minus 2 times gy3, and plus minus, of course. So that is going to give me, when I substitute the known values, that v final is plus or minus 10 meters per second. So what does that mean? It means that the bow passes that position 15 meters above the release point, or above where the bow leaves the hand, 2 times. Once going up, that is the positive solution, and once going down, that is the negative solution. As I said at the beginning, the bow does not stop at 15 meters above, it continues to go up. Now let's look at the following example. Your cousin, Throckmorton, skateboards from rest down a curved frictionless ramp. If we treat Throcky and his skateboard as a particle, he moves through a quarter circle with radius of 3 meters. And Throcky and his skateboard have a total mass of 25 kilograms. First, find the speed at the bottom of the ramp, and second, find the normal force that acts on him at the bottom of the curve. So for the first part of the problem, I'm going to use conservation of mechanical energy one more time, since there are no non-conservative forces present in the system being the buoy and the ramp. There is no friction, therefore there are no non-conservative forces here. So conservation of mechanical energy applies. Delta E mechanical will be equal to 0. For calculating the potential energy terms, I'm going to select my reference level to be at the bottom of the ramp. So at the top of the ramp, the potential energy will not be 0, the kinetic energy will be 0. At the bottom of the ramp, the potential energy will be 0, but the kinetic energy will be not 0. So the initial kinetic energy is 0, and the final potential energy is 0. So from here, I can calculate the velocity. Also, let's cancel the masses on both sides. And what we get for the final velocity looks like this. V final is square root of 2 times g y initial. Y initial is simply the radius of the ramp. If we go back, y initial is the distance from the top of the ramp to the ground, which is the radius of the ramp. So then this simply becomes square root of 2 times gr. Let's substitute the values and see what the final velocity is equal to. The final velocity is equal to 7.67 meters per second. The second part of the question was to find the normal force that the buoy experiences at the bottom of the ramp. So at the beginning of the motion, the normal force is 0, and only the weight of the buoy is present that pulls straight down. And as the buoy starts to take or go around the curve of the ramp, normal force appears, and it always points towards the center of the curve. So at the bottom, the normal force points straight up, the weight straight down. So one more time, at the bottom of the ramp, there are two forces that act on the buoy or that are present in the system, that's the normal force, and the weight of the buoy. So the net force determined by those two would be the centripetal force for the problem. The centripetal force points, of course, towards the center of this circular ramp. So the net force in y direction is also the centripetal force, and this is equal to the normal force minus the weight. And now the centripetal force, of course, also equal to the mass of the buoy skateboard times the centripetal acceleration. For the centripetal acceleration, we have a relationship between that and the velocity of motion around the circular trajectory. The centripetal acceleration was equal to v squared divided by the radius of the trajectory. So in our problem, v is the final velocity of the buoy at the bottom of the ramp. So the centripetal acceleration will be v final squared divided by the radius. But v final squared, we found, was equal to 2 times gr. So combining the two gives me that the centripetal acceleration is equal to 2 times gr divided by r, or that is 2 times g. So let's now combine everything together. We have that the normal force minus w but minus the weight is equal to mass times centripetal acceleration, or in other words, 2 times mg. So then the normal force is simply 2 times mg plus w, or this is 2 times mg plus mg, or this is 3 times mg. Substituting the mass of the buoy, which is 25 kilograms, gives us that the normal force is equal to 3 times 25 kilograms times 9.8 meters per second squared. That gives us 735 newtons for the normal force. Now let's apply the knowledge that we gained from this chapter in a situation where we have an object attached to a spring. So we have a glider with mass of 2.2 kilograms. It sits on a frictionless horizontal air track, and it's connected to a spring with a force constant or spring constant K equal to 5 newtons per meter. You pull on the glider, stretching the spring by 0.1 meters, and release it from rest. The glider moves back towards its equilibrium position. The question is, what is the x velocity when x is equal to 0.08 meters? So here is the sketch of the situation. The block or the glider is pulled 0.1 meters from equilibrium, then it's released. The question is, what's the velocity of the glider when it is 0.08 meters from its equilibrium position? This is a problem about application of conservation of mechanical energy. One more time. There is no friction, therefore the mechanical energy of the system is conserved. So delta E mechanical is equal to 0. So now, what is the mechanical energy of the system? That is the sum of kinetic energy of the glider plus the elastic potential energy of the spring. So then I can say that kinetic energy initial plus elastic potential energy initial is equal to kinetic energy final plus elastic potential energy final. Kinetic energy initial is 0 because the glider starts from stop or from rest, and the two elastic potential energy terms are not equal to 0. So now let's explicitly write the energy relationship and see what we can get from it. So explicitly written, the energy relationship looks like so. 1/2 kx initial squared is equal to mv final squared over 2 plus 1/2 kx final squared. I'm looking for the velocity at the final position of 0.08 meters from the relaxed or equilibrium position of the spring. So we get the kinetic energy mvf squared over 2 is equal to 1/2 kxi squared minus 1/2 kxf squared. 1/2 kxi squared is equal to 0.025 joules. and 1/2 kx final squared is equal to 0.016 joules. Or in other words, the kinetic energy mv final squared over 2 is equal to 0.009 joules. Now let's solve for v final. So v final is equal to plus or minus square root of 2 times 0.009 joules divided by 0.2 kilograms, or this is plus or minus 0.3 meters per second. We here must select the negative solution because this glider is going in negative direction. So v final is equal to minus 0.3 meters per second. Now let's look at the same situation with the glider from the previous example, but now there is a constant force F of 0.61 newtons in positive x direction applied to the glider. The question is, what's the velocity when the glider has moved 2.1 meters from the equilibrium or relaxed state of the spring? So this again is an example of application of conservation of energy when external force is applied to the system. This means that the work done by the external force F is equal to the initial kinetic energy of the glider plus the initial elastic potential energy of the spring should be equal to the final kinetic energy of the glider plus the final elastic potential energy of the spring. Let's write explicitly the expressions for those energies. The work done by the external force is equal to force times displacement and times the cosine of the angle between them, which is 0, so that's a 1. That's why I skipped it. The displacement is 0.1 meters. The initial velocity of the glider is 0, so this term here is a 0. The glider initially is at the relaxed position of the spring, so this is also equal to 0. I'm looking for the final velocity, and the final position is 0.1 meters. So now let's solve for the velocity. The elastic potential energy at the final position is equal to 0.025 joules. The work done by the external force is 0.061 joules. And the final velocity is plus or minus square root of 2 times the difference between the elastic potential energy value and the work done by the force divided by the mass of the glider, which gives us plus or minus 0.6 meters per second. The negative solution here corresponds to the glider going to the left, but we know that the force is applied in positive x direction, so that means that only the positive solution can be the correct solution for this problem, and so V final is 0.6 meters per second. With this, I'm going to conclude the lecture on potential energy and conservation of energy.